Hi, welcome to Probabilistic Programming 3. Today we'll be doing regression and classification. This video is on regression and the next video is on classification. So we'll be tackling a problem of economic growth today. So in 2008 the credit crisis in the US sparked an international recession across many countries. The year is now 2011 and the Turkish government has asked you to determine whether Turkey is still in recession or not. You decide to have a look at the data of the National Stock Exchange and determine whether there's a positive or negative trend in there. This is the third probabilistic programming session. By now I'm assuming that you're familiar with some commands in Julia. So in this case we're using certain software packages such as CSV and plots and stuff. And here we're using CSV to read a data file. So this is actually a data set from an online bank of data sets. It's called the UCI ML repository. We have daily measurements from the Istanbul Stock Exchange from the 5th of January 2009 until the 22nd of February 2011. So you can see that here we have a series of dates and we have the closing value of the ISE for that particular date. So I'm going to look at a particular time period in that data set, the 436th up until the 536th sample. These are the last 100 samples. So if I plot those values over time, you can see here on the x-axis the dates, the 27th of February the 27th of September 2010 up until the 22nd of February 2011, and on the y-axis we have stock market levels. You can see that there's quite a lot of variation in these levels. So we're going to apply a regression model to this data to determine, as I said earlier, a positive or a negative trend. So the model specification part, we have input data x, in this case the dates, and we are going to refer to that as covariates, and we have output data y, in this case the stock exchange levels, which we're going to refer to as responses. A regression model has parameter theta used to predict y from x. And what we're looking for is the posterior distribution of these parameters theta given the observed data y and x, which we say is proportional to the likelihood times the prior. So the likelihood of y given x and theta times the prior for theta. We assume each observation yi is generated via a linear function of xi and e, some noise. To be precise, e is white noise, Gaussian distributed, centered at 0, with some noise component sigma y. The regression function f of theta is linear, so we take an incoming covariate and then you multiply that with a theta 1, which is a slope coefficient, and we add a theta 2, which is an intercept. We bundle these two parameters, theta 1, theta 2, into a parameter vector theta, and in practice we also augment this data matrix x with a 1 for each observation, so that you may be able to write this regression function as the dot product between theta and x. So if you integrate out this noise e, then you obtain a Gaussian likelihood function for the ith response centered at the regression function applied to the ith covariate, with the noise variance as the likelihood variance. So we know, so that settles the likelihood part of this equation, and now we'll move on to the prior. We know that these classification parameters theta can be both negative and positive, and we know that they're real valued, so it makes sense to apply a Gaussian prior to that. So theta is distributed as a Gaussian with mu theta and sigma theta. For now, this is all we need. Those are two components in our model. To cast this in Formulab, we're going to start a factor graph, and then we're going to define a factor node f of a of theta, corresponding to the prior, and a second set of factor nodes f of b of theta corresponding to the likelihood part. I say set of factor nodes because we're actually performing a number of operations here. We have the clamped variable xi, then we have the dot product with with the unknown variable theta, and then we get the response yi. And we also have this clamped noise variance parameter. But we'll see below that once we visualize the graph, we see that it's mostly about f of a of theta, the prior, and f of b of theta, the likelihood. So note that theta is the only unknown variable here. The other variables are known. X and y are observed, and mu theta, sigma theta, and sigma y are clamped. So if you define this model in Formulab, we get so we define the prior weight parameters to be well, we're going to use a unit Gaussian for that, so centered at 0 with an identity covariance matrix. For now, we're setting this noise variance parameter to 1. This has not been fit on the data, and so this might be a poor choice. In practice, you might want to set up another prior for this unknown variable and then infer it simultaneously. We're not going to do that here. We're just going to show how a regression model works. Then we define a variable theta, which we say is distributed as a Gaussian, parameterized by mean and variance, namely mu of theta and sigma theta that we defined here. And then we give it some ID, namely f of a. The covariates x are just going to be defined as a random variable without a specification, and later on we say that they are observed. For the likelihood, we say that y is distributed as a Gaussian parameterized by mean and variance. Its mean is the dot product between x and theta, and its variance is this noise variance parameter. So that means that this one is clamped. The idea that it's given is f of b, as described here. So y is also observed, and if we then draw the graph, we get, let me just zoom out for a bit. We get something that is not too complicated. We have an FA prior node with two clamped parameters, mu of theta and sigma of theta. We have this unknown variable theta. Then we have the dot product between theta and x, which produces this temporary variable, variable 1, and which variable 1 is fed to this likelihood node f of b together with the clamped noise variance to produce the response y, which is observed. X is also observed. So remember that the difference between an observed variable is that we assign a placeholder there, and the variables that the parameters that we set, that we make choices for, those are deemed clamped. So we've clamped 1, 2, and 3, and placeholder x and y. But this is only for a single observation. This is the graph for a single observation. You saw in the previous probabilistic programming session where we had these questions. So we had two questions. We had two likelihood parts and an equality node feeding into the unknown variable, the parameter. And actually in this data set we have 100 samples, so we're actually going to do the exactly same thing. We're going to repeat this likelihood subgraph n times, 100 times, and all of that will feed into an equality node that is attached to theta, which is attached to the prior node. This is a bit more this takes a bit more syntax to define that graph. Parts of the graph specification are still exactly the same, but we now have a vector of variables x of size 100 and a of length 100. And we have a vector of variables for y of length 100. And we now iterate over all of these samples to define the ith entry of x to be just a random variable, and the ith entry of y to be Gaussian distributed, parameterized by mean and variance, which then takes the dot product of theta and the ith component of x. Here, so we still use this this noise variance component for the likelihood, and in here we're building a string f of bi, so the ith likelihood node, and we're casting that into a symbol. And if you remember, a symbol is a reference to a variable, so that's a colon and then some variable name. So we're going to say that the ith x and the ith y are observed, and we tell Formulab that it can use the that it's indexed at a particular point. So if you draw this graph, you get quite a large snake-like object, which is very hard to parse. It's so small you can't see what's happening. But essentially what we're doing is we're taking this graph and then repeating this likelihood subgraph structure 100 times, and all of those connect to the equality node. Yeah, so algorithm compilation stays exactly the same as before. We just have one unknown variable theta, and then we generate an algorithm source code, and then we bring that source code into scope. And now we have access to this step function that we can use to update parameters. So here I'm going to feed in data. I'm going to initialize a data dictionary to store the posterior estimate for theta. As for the data, I'm feeding in all the data at once. So I have x and y for the covariance and responses. In this case, I am changing x somewhat to suit Formulab's needs. Excuse me. So Formulab indexes into this data x structure, but it uses a single index. So I can't put in a matrix here because it doesn't know whether to take the ith row or the ith column. So what we're doing is this is called a list comprehension. If you're familiar with the concept in Python, then this is entirely the same. What we're doing is we're iterating over all of these samples, and then for each sample we're creating a column vector. And so this is a list of column vectors. So if you go to the ith entry in that list, that gives you column vector of the ith observation. Considering that the stock values are, that's already a vector, that's univariate, and so we can actually go to the ith entry there and get the ith response. So we don't need to perform that trick here. And then we execute this step function to update our posterior for theta. If we then visualize the transition from prior to posterior for the parameters, you can see that it has changed quite a bit. This is our prior, the x-axis is theta 1, the y-axis is theta 2. We specified our prior to be centered at 0 with an identity covariance matrix, and you can see that the probability at the peak levels off at 0.16 somewhat. The situation for the posterior is vastly different. It's much more sharply peaked. You can see that it's the band for theta 1 is very narrow. For theta 2 it's a bit more uncertain. It's a bit less sharply peaked. So you get this vertical ellipse. And you can see that the peak of probability here has a really large value. It's really sharply peaked there. It's centered on a very small area of parameter space. And just as a reminder, this is a Gaussian distribution, so a continuous probability distribution. Continuous probabilities or probability densities can be larger than 1. The only requirement for a density, a continuous probability distribution function, is that it integrates to 1, which is still the case here. So we are using a point estimate for now. Sorry, we are using a point estimate for now to compute the regression function and make some prediction. I am going to ask you to compute and visualize the full predictive distribution, but I'm leaving that for the PP assignment because I want you to get your hands dirty and dive into that. So if we extract the mode from the posterior for theta, so that gives us theta map, then we can generate this regression, this estimated regression function with by multiplying the dates with the estimated slope coefficient and then adding the intercept. If we print the slope coefficient, we can already see that it's negative, so that should already answer our question, namely that that the stock market is experiencing a negative linear trend. So we visualize that here. We can see that more clearly. Over the course of September 2010 up until February 2011, the stock exchange is declining. And if, so assuming the stock market is an indicator of economic growth, then we may conclude that the Turkish economy is still in recession as of March 2011. Right, so then we get to this try for yourself block. So in the beginning I specified this time period variable. Let me just go up for a bit. So for convenience sake, I chose the last 100 samples. I want you to change this. Have a look at the other periods in this data set. Perhaps look at a longer time frame instead of 2 quarters. Look at a whole year, and see how that changes your results and your conclusions. Should you change this time period variable to span the entire range of January 2009 up until February 2011, you're gonna find out that inference in this model is quite slow, or it takes quite a long time, because well, you can imagine why that happens. We're repeating the same subgraph structure. Well, here we repeated it 100 times, but if you take the entire data set, then you're repeating that 536 times. And so Formula passes messages for all edges in that graph. So that's quite a lot of computation that's occurring. And there's as well there's a scheduler in Formulab internally that computes which messages have to be sent where. So that takes a while. Oh, sorry. I went too far. So there's an alternative way to do inference in exactly the same model, which is a bit well, quite a lot faster, but it's not mathematically equivalent. You'll get slightly worse estimates. So it's called recursive estimation, and what you do there is you're essentially you make an observation, you update your posterior, then your posterior becomes the prior for the next iteration, and then you make another observation, and then you update your posterior with your prior and likelihood, and then you move on to the next observation. Your posterior has become your prior again, and you make another observation, do another posterior estimate, etc. So if we want to do that, if we want to do some recursive estimation for this linear regression model, then we can define the same graph as I mentioned earlier. It is exactly the same graph, except for the fact that we've now, instead of clamping the parameters to the weight prior, I'm actually using placeholders here, which means that I'm going to feed in data. And what I'm going to do is, we'll see this a bit later on, the first placeholder values are going to be the prior parameters that we initially specified, so zero, mean, and identity covariance matrix. And then as we move through the data, we're just going to take the previous posterior estimate and then feed that into the parameters of the prior. Outside of that, the model is exactly the same. So we still have a prior node f of a with two, well, they're not clamped now, but they're two placeholder parameters. And then we have x, the dot product between theta and x produces this temporary variable, and then we have this f of b where we generate this response, and we still have the same clamped noise variance. The algorithm compilation is also still exactly the same, and if we now execute the algorithm, you can see I have again initialized a data structure for to house the posterior, and I'm now assigning it an initial value. I'm saying that the posterior for theta is a probability distribution which is multivariate, Gaussian, parameterized by mean and variance, and I say that its mean is a vector of zeros, and its variance is an identity matrix. So then we'll move through each of these samples, and so for each sample I am feeding in the current date augmented with a 1, and then the current response, and then I'm feeding in the for mu of theta the mean of the previously estimated posterior, and for sigma of theta I'm feeding in the covariance of the previously estimated posterior, and then I make an update to the posterior, and then so you move through all of these samples in that fashion. So you're going to find out, if you set this time period to a larger value, you're going to find out that this is much faster than before. However, it's not going to produce exactly the same result. Recursive estimation is not mathematically equivalent to non-recursive estimation. And if you're familiar with that, it's sort of like the difference between filtering and smoothing. And so if you visualize the estimates, you can see that, well, the prior is still the same. Posterior has the same shape, namely that it covers a very narrow band in theta 1 and a bit wider band in theta 2. But you can see that the peak of this distribution lies at 240, which is well, it's a bit lower than 300. So you're a bit less certain, you have a little less confidence in your estimates. Alright, so that covers the regression part. In the next video we're going to look at classification, specifically a credit assignment problem. So I hope to see you there.